6.7, Day 2. We'll do a little bit of application, and then we'll find the sum of a geometric series. Finally, we'll use logarithms as a means to find the number of terms in a geometric sequence. Here's a little application. A phone tree is when one person calls a certain number of people. Then those people call the same number of people, and so on. In the fifth round of calls of this particular phone tree, 243 people are called. Write an explicit definition for the number of people called in each round. How many people would be called in the eighth round? If we're asked to write an explicit definition, this is from our notes from yesterday. We would start off with a sub n equals a sub 1 times r to the n minus 1. And then we need to determine how many people are in the first round, and then what the rule is for each additional round. Well, notice in that first row, or in that first grouping, the call is out to 3 people. So that would be that first element within this phone tree. 3 people are called. From there, they call a certain number of people, and so on. To figure out how many people, or what the rule is each time, we can use the fact that in the fifth round, there are 243 people. So using that information, if we start off with a sub 1 equals 3, I'll substitute that into my formula. A sub n equals 3 times r to the n minus 1. To get r, we can then use the a sub 5 and 243. If the fifth round means n equals 5, then we know we have 243 people. If I substitute those values in, now I have 243 equals a sub 1, which is 3, times r to the 5 minus 1 power. Now we need to solve for r. I'm going to have to run over into the space over here on the right a little bit. If we have 243 on the left, equals 3 times r to the 5 minus 1 fourth power. Now let's just solve for r. If I divide both sides by 3, 243 divided by 3 is 81, equals r to the fourth power. Using your power chart or typing in 81 to the 1/4 power, this means r also equals 3. That means each person is calling 3 more people. And you could maybe even see that within that pattern on the right. Our formula then, and I've totally run out of room here, so I'm going to give myself a little bit more space. Slide this over a little bit. Our formula would then be a sub n equals a sub 1, which is 3, times our pattern calling 3 people to the n minus 1 power. And remember, for an explicit formula, this is valid for when n is greater than or equal to 1. Now, using that information, how many people would be called in the 8th round? That means n equals 8. So if n equals 8, then a sub 8 equals 3 times 3 to the 8 minus 1 power, which would be 3 to the 3, or times 3 to the 7th power. And if you plug that into your calculator, in the 8th round, 6,561 people would be called. So there's just a little bit of application. Next, we're asked to write the expanded form of a series. Now, a series is just the numbers in a sequence with pluses in between. Notice we have sigma notation, so we're bringing that back. To write the expanded form, we need to know what the 7 terms are. And we know there are 7 terms because sigma goes from 1 to 7. So let's first list out our terms. A sub 1, we would get simply by plugging in 1 for n in the formula. 3 times 2/3 to the 1 minus 1. Well, 1 minus 1 is 0. 2/3 to the 0 is just 1, and 1 times 3 is 3. You maybe even recognize the first term as 3 based on that formula. To get the second term, if we plug in 2, 3 times 2/3 to the 2 minus 1 power. Well, 2 minus 1 is 1. 2/3 to the first power is 2/3. 2/3 times 3 would equal 2. So notice we're just multiplying by 2/3 each time. A sub 3, same idea. 3 times 2/3 to the 3 minus 1 would be 3 times 2/3 squared, which is 4/9, which would equal 4/3 when we multiply them together. If we continue on, and I'm running out of space, so I'm just going to tell you what those answers would be. If we kept plugging in n, a sub 4 would be 8/9. A sub 5 would be 16/27. A sub 6 would be 32/81. And a sub 7, that final term, would be 64 over 243. Notice we're just taking the terms and multiplying them by 2/3 to get the next term. Now that's just listing the terms. What we need to do from here is write the expanded form, and I am totally out of space, so hopefully you'll have some room to write here. The expanded form is simply when you write them out with plus signs in between. 3 plus 2 plus 4/3, and so on. 8/9, 16/27, 32/81, whoa boy, and 64 over 243. Now, if you were to add them all together, you'd need to get a common denominator in order to find the sum. That would be pretty intense. Instead, let's use the sum for a geometric series formula, which is also pretty intense, but it wouldn't require all the common denominators. So let's go back over to the left-hand side of our note packet. The formula to find the sum of a geometric series is S sub n equals a sub 1 times 1 minus r to the n all over 1 minus r. Notice this is an exponential formula, and we can use this formula to find the sum of that geometric series in example 3a. To find the sum, if we know what our terms are, we can use our formula. We know n equals 7, as it says 7, or from 1 to 7 in our sigma notation. We know a sub 1 is the first term, which is 3, and we know our ratio is 2/3. We're multiplying by 2/3 each time. Therefore, the sum of these 7 terms is that really big formula. A sub 1 times 1 minus r to the n power. Yes, we're doing that exponent. All over 1 minus r. And we just simplify, which sounds pretty intense, I know. On the inside of the parenthesis, if we raise 2/3 to the 7th power, that's just 2 to the 7th power over 3 to the 7th power. And that would give us 128 over 2,187. And the denominator, 1 minus 2/3, is 1/3. Now let's get a common denominator in the parentheses. And that would give us 3 times 2187 over 2187 minus 128 over 2187 all over 1/3. And now if we combine the parenthesis on the inside, we get 3 times 2059 over 2187, all divided by 1/3. Well, instead of dividing by 1/3, let's multiply by the reciprocal. We'll do the keep, switch, flip rule here. Sliding this over, whoa, a little bit more. I know, this takes quite a bit of time, doesn't it? So if we do 3 times 2059 over 2187, and then instead of divided by 1/3, we'll do times 3 over 1. The 3's on the outside give us 9. And that would be 9 times 2059 over 2187. Whew, 9 actually goes into 2,187 243 times. Therefore, the sum of those 7 terms is 2,059 over 243. Notice that's the exact answer. So if it says write your sum as a fraction, unfortunately we can't plug this all in on our calculator to get a decimal result. Now, you might be asking yourself, why is this lesson in topic 6b? It's exponential functions, so I guess we see the exponents, but where do the logarithms come into play? In problems like 4a and 4b. When you're asked to determine how many terms there are in a geometric sequence, the process is different from what we did for arithmetic. Remember when we did last term minus first term divided by d plus 1? That was a crazy formula way back in our first topic. Well, this formula is going to be just as interesting. How many terms are in the geometric sequence 200 plus 300 plus 450 plus ... plus 7,688.7? We need to know how many numbers are in that ... kind of grouping to figure out how many terms there are total in that sequence. Here's what we do. We figure out our first term and our common ratio. Our first term is 200, so that's easy enough. To get that common ratio though, remember our formula from day 1. We take the second term divided by the first term. 300 divided by 200 is 1.5. Now we don't have to test it each time because it does tell us in the directions this is a geometric sequence. So the second term divided by the first term would be our ratio each time. Once you know a sub 1 and r, we come up with our explicit formula. A sub n equals 200 times 1.5 to the n minus 1 power. Now we know the last term is 7,688.7, but we just don't know what term value we have there. And all of a sudden, we just have an exponential equation. Let's solve. To solve here, we want to isolate our base, and our base is 1.5 to the n minus 1 power. I'm going to start simply by dividing both sides by 200. If I take 7,688.7 divided by 200, I would get a pretty big decimal, or actually a pretty big number past the decimal. I would get approximately 38 point, and I'm going to go out 4 places, 4435. And on the right-hand side, 1.5 to the n minus 1 power. What I'm going to do now is take the logarithm of each side, apply that property. The log of 38.4435 is equal to, and then I'm just going to write it out as, on the right-hand side, the log of 1.5 to the n minus 1 power. What this allows us to do, if you remember, is takes that n minus 1 and puts it out in front, applying that power property. That gives us log, whoa, I don't know where that came from. We don't want a highlighter there. That gives us log of 38.4435 equals n minus 1 times log 1.5. Move the log over by dividing. We'll divide both sides by log 1.5. When we do that, the logs, whoops, sorry, what's going on there? When we do that, the logs cancel out, and on the left-hand side, we have log 38.4435 divided by log 1.5. Now, when I typed that in, I got 9.0000 something. So that's going to be approximately 9 for our purposes. And if we have n minus 1 on the left, we'll just add 1 to get n by itself. That means there are 10 terms in that sequence. And that's how you use logarithms as a means to help in these geometric models. That will be it for now. We'll cover this additional problem tomorrow, and then you'll have your Pearson assignment.